Hey folks, and welcome back to our discussion of factorial designs. So as we talked about last time, hi Earl. Sometimes you never know what's going to happen. So Earl's going to stand on my leg as I kind of remind you about what we were talking about in the last lecture. So if we have a factorial design such as the kind here, which is called a 2x2 factorial, so we've got two different variables. One variable has two levels, either room temperature or high temperature. And then we cross that with another independent variable, humidity, either low humidity or high humidity. That basically leaves us with four different experimental conditions. So here's where it gets really interesting. There are a lot of different ways that we can actually run this factorial. So one of the things that we can do is do a between subjects factorial. Each participant only takes part in one condition. You can see a similar sort of setup here with the Bartholow and Hines study looking at full between subjects factorial or an independent groups design. So here we have one group that is basically getting the alcohol photos with neutral words. We have another group here that is getting a plant photo with neutral words. Here we get aggression related words and an alcohol photo. And here we have aggression-related words with a plant photo. So we can make sure that each participant is only in one of those four conditions. And in this particular case, if we have 12 people per condition and we have four different groups, that leads to 48 different participants. Now, on the other hand, and this is how I tend to do a lot of my studies, you can do a total within subjects factorial. So in this case, we have everybody takes part in all four conditions. So these same 12 participants will get an alcohol photo with neutral words. They will also get a plant photo with neutral words and an alcohol photo with aggression words and a plant photo with aggression words. So everybody gets exposed to all four conditions. So participants will take part in every condition. As you can kind of see here, again, one of the great things about within subjects designs and with a within subjects factorial is you can make do with fewer people because you've got more data points per participant. Everybody's functioning as their own control. Please make sure that you are using counterbalancing and randomization as much as possible so you don't have to worry about things like carryover effects, progressive effects like or order effects like practice effects or fatigue effects. Now, you can actually make things more complicated if you want. What if I want two different groups? So I want one group that is always getting exposed to a 68 degree temperature. Remember, we're in Fahrenheit here. And one group that gets 95 degrees, like in my temperature experiment. And let's say that both groups are exposed to both levels of humidity. So in this particular case, I've divided people up into groups based on temperature, but everybody gets exposed to all possible levels of humidity. So basically what I've done is I've made temperature a between subjects variable, and I've made humidity a within subjects one. And this is what is called either a mixed factors design or a mixed design. So in the Bartholow and Hines example, maybe we have one group of people, so about 24 people, that are always getting neutral words. They always get neutral word, or they get an alcohol photo and they get either neutral words and aggression related words. So it's the same group of people. They're just getting, so we're basically making the between subjects factor of the photo, either the alcohol or the plant. So this group is getting the alcohol photo, this group is getting the plant photo. And regardless of what group you're in, everybody is exposed to either neutral words or aggression related words. Now you will need more people than you needed in a within subjects design, but certainly not as many as you would require for a between subjects design. Now, in other instances, you're going to have to use a mixed factors design, not because you chose to, but because one of your variables is something that you can't divide people, you can't randomly assign people to. So for example, going back to younger and older drivers and cell phone use, I have to make age a between subjects factor. I can't basically randomly assign somebody to be older or younger. I can't manipulate that myself. So that automatically becomes a between subjects factor. Another example could be looking at gender and mental rotation. I can't manipulate gender. I can't. But I can expose everybody to all possible angles of rotation of different objects. So that'll kind of function as my within subjects variable. But because I'm dividing people into groups on the basis of gender, and I do apologize, I am using a gender binary. Obviously, it's not that simple. But if I divide people into male versus female, that's not something I can randomly assign. And because of that, it has to be my between subjects factor. So if you're using a subjects variable like age, gender, socioeconomic status, marital status, anything like that, you have to do a mixed factors design by necessity, because those subject variables can't be manipulated, they can't be randomly assigned, they're always going to be a between subjects factor. So I want to very briefly talk a little bit about factorial design notation. You're going to see this a lot in journal articles, and you're going to see this in your textbooks. I need to just make sure that we are very clear on what we mean by a 2x2 design. So you hear me calling it a 2x2. So how many numbers are listed are the number of independent variables that you have. So here I've got one number, here I've got another number. So here, because I have these two different digits, that means I've got two independent variables. Now the actual number is how many levels or conditions that particular IV has. So this one is a 2, which means that this variable has two conditions or two levels. And this second variable also has two conditions or two variables. Now here's another example. Let's say, for example, we did a study that was determined to be a 2x2x4 factorial design. How many independent variables do we have here? Well, we have to think about how many digits there are. So let's count them. I've got 1, I've got 2, and I've got 3. So because I've got 3 digits, I know that I have 3 independent variables. How many levels are in each? For my first independent variable, there are 2. For my second independent variable, also 2. For my third independent variable, I actually have 4. So this is how we talk about factorial designs. Make sure that you have a pretty good understanding of this. This is the kind of thing I like to quiz on occasionally. Thankfully, you can take the quiz as many times as you want before the deadline, and I do take your highest score. So hopefully, if this is a little tricky, practice. You will get better. So what are some of the advantages of a factorial design? And I've already kind of talked about this a little bit. In the world, variables and different factors interact with each other. For example, if you're taking drugs and behavior with me in the fall, we're going to talk about how drugs interact with other drugs. It's why you really shouldn't have something like a Red Bull cocktail. The effect of alcohol counteracts and interacts with the effects of caffeine. We'll talk about some of the interactions between coffee and cigarettes. We'll talk about some of the interactions between things like antidepressants and alcohol, or anxiolytics, like anti-anxiety drugs and alcohol. All of these are interactive effects. Things interact with each other all the time. So when you use a factorial design, it actually has more external validity because the world is full of interactions and you are doing an experimental study. that is looking at interactions. So you're able to account for more complex relationships between variables that you otherwise wouldn't have. So when we talk about some of the different effects of factorial designs, there are two main things that we are going to be looking for. So let's say we're doing a very simple 2x2 factorial, like a lot of the ones we've been looking at so far. So when we do a 2x2 factorial design, there are three effects that are possible. There's a main effect for each of our independent variables. So let's say we're talking about gender and mental rotation. So one variable is gender, the other is angle of rotation. So I have two main effects. So a main effect is when an independent variable has an overall effect on the dependent variable. So it's kind of like what we saw for our single factor design. So for example, alcohol has an effect on aggression. In a factorial design, that would simply be considered a main effect. In our gender and mental rotation example, so mental rotation performance accuracy is our dependent variable. Our two independent variables are gender and the angle of rotation. So when I do a 2x2 factorial design, gender, I can find a main effect of gender or not. So there may be an effect of gender on performance. There could be an effect of the angle of rotation or not. So we're going to look for those two main effects. And then we're also going to look for an interaction. And because our independent variables can interact, this is what makes factorial designs so much more powerful and so much more preferred than a single factor design. So like I've been mentioning, let's talk about the example of antidepressants and alcohol. Now, neither of those may have a very big effect on their own. Maybe the antidepressants effect on its own is pretty modest. Maybe the amount of alcohol that you're drinking is not enough to have an effect. But if you combine those, they might interact with each other and have a bigger effect than each of them would on their own. So one of the benefits and one of the biggest advantages of a factorial design is what we call an interaction. The way that one independent variable influences behavior differs depending on the level of another independent variable. Now that sounds really vague. Don't worry. We're going to get a lot of opportunity to think this through and practice. And you all know that you're welcome to ask me questions on the Discord or on email anytime you want. So here's an example. So here's a really simple fake data set that I made looking at gender and angle of rotation, and then accuracy, mental rotation performance is our dependent variable. So here is the data from my female participants. So here is performance for 45 degrees of rotation. Here is performance for 180 degrees. Now, here's what's really critical. It's possible here that there is a main effect of gender. Possibly. I don't know if it's statistically significant, but it looks like there could be an effect here. Why? Because my performance for males, so my male participants, are always performing better than my female participants, regardless of angle of rotation. They're always doing better. Odds are pretty good too. There's probably an effect of angle of rotation. How do I know this? If I can kind of collapse across my male and female performance, in general, accuracy for 45 degrees, if I take the average of these 2 points, it's probably going to be right here, right in the middle. Performance for 45 degrees angles of rotation is much higher than it is for 180 degrees, so there's probably an effective angle of rotation here. But most importantly, there's an interaction here. Now, how do I know that? Look at my gender effect over angle of rotation. So notice here that my male participants have a slight advantage over my female participants at 45 degrees, but look at how much that gender effect widens when I'm at 180 degrees. So basically, these variables are interacting with each other. The gender effect increases with increasing angle of rotation. Now, one of the tricks for knowing if you have an interaction, are these lines parallel? No, not at all. Generally, you can tell that you have an interaction in a graph if your lines either cross over or if they are not parallel. And these lines are definitely not parallel. Now, this particular type of interaction, we'll talk about this a little bit more. Your textbook calls this a spreading interaction. Another way that you can talk about this is something called an ordinal interaction. So we'll get to talking more about main effects and how to identify them, and interactions and how to identify them in a few minutes. But let's talk a little bit about the drawbacks with factorial designs. Now, in general, factorial designs have a lot of good benefits. One of the big downsides is that the more independent variables you have and the more conditions per independent variable, you have to have more experimental conditions, because remember, you have to cross all of the levels of independent variables with each other. So if I have a 2 by 2 factorial, I've got 4 conditions. If I've got a 2 by 2 by 4 factorial, I've got 16 conditions. And the more conditions you have, the more participants you will need. If you're doing a within subjects design, you don't necessarily need more participants, but you might need to collect more data from each participant. So the more conditions you have, the more data you need. And that means either more participants or more time with a single participant for those within subjects designs. So how do we design factorial experiments? Here are a couple of things to consider. So here's some more fake data. And you'll notice here, again, we're looking at mental rotation accuracy. We're looking across gender. But in this case, I've added more possible angles of rotation. So something you need to consider is, how many independent variables do you want? Do you want to add more? And do you want to add more levels? And one of the big questions you have to ask yourself is the effect that you're interested in something that is non-linear? So are we dealing with an effect that may not be linear in nature? So for example, looking at angle of rotation, maybe we find that performance for mental rotation performance is really good up to 90 degrees, and then it tanks. Well, that's a non-linear effect, and in that case, I probably need more than 2 conditions. So if you are interested in an effect that has been demonstrated to be non-linear, you need at least 3 levels of an independent variable. If you only have 2, what are you going to get when you have 2 points? You're always going to get a line. So if you know that the data that you're looking at may not be linear, make sure you have at least 3 levels of that independent variable of interest. So if we know ahead of time that this is not linear, we don't just want to have 2 data points. We're going to need more. Now, I do want to get back to talking about those subject variables. Now, as I mentioned in the last lecture, if you've got, or actually it might have been at the beginning of this one, I'm losing track of time. If you have a subject variable like age, gender, ethnicity, race, socioeconomic status, you have to do a mixed factor design. That has to be a between subjects factor because you cannot manipulate it. So now other sources, so this is obviously a mixed factors design. This could, other people refer to this as a person. So the subject variable by situation, our other independent variable of interest, factorial design. Now, you are not limited to 2 subject variable levels. You can have as many as you need. Just remember that the more levels that you have, the more data you are required to collect. Now, here are a couple of things to keep in mind anytime that you're messing around with subject variables in your experiments. Remember that you cannot manipulate them. You did not manipulate that variable. So because of that, you need to be very careful in your conclusions. So for example, I do a lot of mixed factor designs and have done a lot of mixed factor designs looking at age effects. So I can't manipulate age. I can't manipulate who is a young adult and who is an older adult in my research studies. And because I can't do that, I have to be very, very careful about the conclusions that I draw. So I can't necessarily say age caused worse performance in memory. I don't know. I didn't manipulate that variable. I can say, however, that age was associated with a decrease in memory. So like I said, you can't manipulate those subject variables. Be very careful about the conclusions that you draw. Make sure you're not being hard-lined with a causal effect. You might have to say that age influenced memory performance, or that it is associated, or even worst case scenario, correlated. But you can't really talk about cause effect here. Additionally, if you are looking at a subject variable, such as looking at gender with mental rotation, try to control for other variables that could potentially explain findings. So for example, it's a pretty robust finding within cognitive psychology that generally women tend to have a harder time with mental rotation than men do. And some of that has at least been, some of that difference is at least partially explained by men's greater experience with spatial rotation in gaming. And so that could be another variable that has nothing to do with gender. So if I can't control for gender, what I can do is control for gaming experience and make sure that my female participants have just as much gaming experience as my male participants do. So that way I'm not introducing a potential confound. All right, so I'm going to go ahead and stop here. We're going to talk some more about looking at factorial designs very soon.